Okay, this is the area of surface area of a Pringles chip. That's what we're trying to work on, right? So I set this all up and gave you a lot of background information here, 3D stuff, blah 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 blah, and the equation I'm using to approximate the Pringles chip and the explanation of the hyperbolic paraboloid and all that stuff. Okay, so I'm scrolling down here, a little more explanation. Here's the formula I'm going to use, which is the surface area formula. Okay, it's basically a projection of a surface area floating in space, and that surface area floating in space is called S. This is your Pringles chip, and it's being projected on a 2D shape right here in the XY plane called D. So when I say this integral, this is the integral across D here of this. This is the formula we're going to use, and these are partial derivatives for your equation. So the equation I'm going to use for this one very specifically is this equation, and I'm going to set it up that way. Okay, so cool. Alright, so what we're going to say here, we're going to do the calculation here. The calculation, so z is a function, you should write this somewhere, of x and y. And that function for me is going to be x squared over 10, or you can call it 1/10 x squared minus 1/10 y squared. Okay, that's what I'm going to say here. And so I'm going to use this formula right here, as I've written, across D, which is your XY plane. D means XY plane, just keep that in mind. This is going to be the square root of 1 plus, what do we have here, dz dx squared plus dy, dz dy. Let me erase that, dz dy squared. These are called partial derivatives, which we're going to be doing. dz dy squared. And then I'm going to take the derivative of y first with respect to y, and the integral with respect to y first, and then I'll do dx. So since I'm doing dy first, taking that integral, this one here will be your y, and this one here will be your x. So we go outside and then work our way outward. We start on the inside rather than work our way outward, is what I mean. So here's what we're going to do here. We're going to take this derivative here with respect to, this is equal to z, with respect to x. When I say dz dx, we're taking the derivative with respect to x as partial derivative, so we're going to treat this y as a constant. It might as well, this whole thing might as well be a number, because y, since we're taking the derivative with respect to x, y doesn't really matter. You could treat y as if it were a number. You could call it like 3. If you just take the derivative of a number, though, if this whole thing is a number, the derivative of that would be 0 anyway. So what I'm saying here is that the derivative of this is going to be 2 times a 10th, which we're going to call a 5th, x. That's it, right there. And then the derivative of this is 0 because we're treating y as a number, as a constant, because we're taking the derivative with respect to x. Okay. All right. So and then we're going to take another partial derivative, which is dz dy. This time we're going to treat x as the constant. So if I take this derivative of this, which is pretending this whole thing is a number or a constant, it's going to be 0. And then what I'll have here is 1/5 or negative 1/5 y. So this is negative 1/5 y. Okay. So we got these things, negative 1/5 y, 1/5 x, and they're going to go into my dz dx dz dy squared. Okay. All right. So this is my process here, and the reason I use this function instead of saying just x squared minus y squared is because if you actually graph x squared minus y squared, it doesn't look like much like a Pringles chip. I mean, the shape is the shape is the same, but the parameters make it look more like this. I should say more like this, much too steep when you draw it, right? Doesn't look like a Pringles chip when you draw it like that. So I didn't do that. So I used this one instead, which is the graph I've made here. It looks much more like a Pringles chip. Okay, that's why I put some parameters on it. It shouldn't matter that much though. Okay, so here's the deal. I had to actually figure out my limits of integration here. Okay, and technically, since you have dimensions of a Pringles chip for your length and your width and all that, you technically could try to make those your limits of integration. Okay, in this case, the length of my chip is going to be my x, the way I've drawn the equation. This will be my x right here, and this actually will be the y right here. Okay, so I'm treating this as x. I'm taking the derivative here, so if this were the center, if you're making that the center, this would have been like negative 3.2 up down here and positive 3.2 if you're calling this the origin right there in the middle. Okay, so because you're on the XY plane when you're looking at it like that. Okay, like right here, that's where the middle would be, and then you would have that. But here's the problem with that integral. So this is what we have. Let me write this down. The difficulty you're going to face with that, and it's actually not a small one. This is going to be 1 plus, we're going to call this 1/5 x squared plus, well, we're squaring this, so this is going to be plus negative 1/5 y squared. So we're squaring it anyway. So let me write that. We're just doing the steps here across D. So this is what I'm saying. Showing you everything I'm doing here. So I'm going to go ahead and square that. It's going to be 1 plus, we can call that x squared over 25 or 1/25 x squared if you want. Doesn't make any difference. And this is going to be y squared over 25. Now the issue here, this is going to be dx, by the way. I don't know why I wrote it like that. The issue here is if you use those limits of integration from the dimensions of the chip onto here, that's going to be a really tough integral to take, actually, just because one of these is a square right here. If this were just a y, we could do it pretty easily, but just the way the equation is set up for the hyperbolic paraboloid, it's just going to be really tough to do that integral. Okay, so to make it simpler, instead of projecting across a rectangle, because that's what I would be doing if I were to do those dimensions, we'd be projecting across a rectangle created by the length and the width. We're making like an imaginary rectangle. Instead of doing that, it's actually a lot easier to project it across a circle. All right. So basically, when you project it across a circle, what you're doing is you're saying what segment of this area here is inside this cylinder. Okay, because if we were to make a circle and then make a third dimension to it and raise it upward, it would create a cylinder like this, right? And this is what it would look like. So I'm asking, what is this area inside of this cylinder as an approximation of the chip? And that's going to be a lot easier. And the reason it's easier is because you can then use polar coordinates and then change your limits of integration that way. So it's going to be infinitely easier to do that. Okay, so here's what I'm going to say. So when I'm talking about polar equations, okay, here's really what's happening. Polar coordinates and polar equations. If I were to say somewhere, I don't know, let's say I have a 3, 4, 5 triangle. Right triangle, this being the origin here. And then you have a coordinate here. So this coordinate would be called 3, 4. Right? And that's a rectangular coordinate system, we call it. It's rectangular. Or you can say Cartesian coordinate, using the Cartesian coordinate system of x-axis and y-axis, okay? And there's another thing called polar coordinates. And this is where, instead of writing this, we're going to change it to polar, or is represented as a radius and an angle, like that. So basically, my radius here, since this is a 3, 4, 5 right triangle, is 5. So I can transfer this to 5, and then you would have some sort of angle here that you can find using basic trigonometry if you had to. And you could write it like that. You could say that's your angle theta, 5 comma theta, whatever that is. And that's a rectangular to polar. It would be something like that, whatever that angle is, right? And that angle could be really found as well, lots of ways you could find it. You could say that it's the tangent inverse of 4/3 or whatever. You could find it like that, okay? All that stuff, right? That's not super important though, because we're not going to really do too much of that for this calculation, but that's just an overview of what polar coordinates mean, all right? But here's really what's going to happen. I'm going to project this across a circle. Now, this circle here, I'm saying I'm going to project this area onto this circle on the XY plane, which is really through a cylinder. If you make it a 3D shape, you're asking what part of this area is inside the cylinder. It's the same concept, okay? So if I ask you what is this area inside the cylinder, it's really asking you the same thing as what is the area on the circle as it's projected onto the circle, okay? So that's interesting. Now, but here's what I'm going to do. To actually make a dimension similar to what that is, I'm just going to make the since this is, I believe this was 4.3 for the width of the chip, so I'm just going to call it 4. So I'm going to make this 2 and make this 2. Losing, you know, 0.3 of a centimeter is really negligible, honestly. So I'm going to make that, and I'll make the calculation simpler. So, oops, I don't want to do that. So I'm going to actually make this a circle with a radius of 2, since this is the shorter side. 4.3, 4.3, I'm just going to make it the whole thing 4 across, so 2 and 2. That'll be the radius of my circle. So the equation of a circle with a radius of 2, since we know the equation of a circle is x squared plus y squared equals r squared, I'm going to make that equation, of course, x squared plus y squared equals 4, because 2 squared is 4. So that's what I'm going to use. I'm going to say, what is the area of your Pringles chip, right, that's inside the cylinder created by this, okay? Or basically projected onto a circle. So now that I have that equation, it's really great, because now I can say, well, that means that y squared is equal to 4 minus x squared, right? And then we could say, well, y is equal to the square root of 4 minus x squared. And actually we could say it's plus or minus that, right? Okay, so now that I have that, I'm going to use this as my limit of integration for y. And for the x, this is actually even easier, because since this, it's even easier because x, since this is a function of x, right? If you think of a circle, right? If I were to draw, actually, you should just draw this circle. You could draw it like this. Okay, and this will be 2, and this will be negative 2. And this will be 2, and this will be negative 2. Oops. For this function, it's a function. Well, it's not really a function, but it's an equation as such, like this. Right? So on the x-axis, it's actually between the boundaries of 2, or negative 2 and 2. So that's going to be your limits of integration for x. And your limits of integration for y, since this is really the equation of the square root of 4 minus x squared, on the top, this part of this equation right here is on the top when you're graphing it in 2D space, and this part of the equation is actually the negative. Let's actually write this in a different color, like this, green. This is the negative of the square root of 4 minus x squared. So basically y is defined by these functions and x is defined by these parameters. So basically what's happening is I am going to make this my limits of integration for x, and this will be my limits, and these two will be my limits of integration for y. Okay, so what I'm telling you is when I set up this integral, my outside will be x. Right here we're doing x on the outside, so the limits are negative 2 and 2. And on the inside integral, it'll be negative root 4 minus x squared and positive root 4 minus x squared. And then we're going to take that integral of this dy dx. Remember that y goes dy I'm doing first, so that's why the limits of integration will be for the y first, right? Inside to inside and then outside to outside. So this is how this works, okay? And I'll post another video kind of show you what just happened. That'll give you an example, a similar example, but not the same as your concept, but similar example, okay? And then, so here's what I got. Okay, and don't forget that's equal to the area of S, okay, projected inside that circle, or basically the area of the Pringles chip, S right here, that's the area of the Pringles chip that's inside the cylinder. Okay, so that's being projected through it, okay? It's the part of the Pringles chip that's inside of the part of the area of the Pringles chip, I should say, that's inside of that cylinder. So remember, back up here, this is the part of the area that's inside the cylinder right there. Okay, that's what I'm saying. Okay. All right, so here we go. Now, the interesting part here is when you're converting to polar. So the polar, we're going to use the equations here. This is basically what happens with polar equations, polar coordinates. When I said this, Sorry to go through this all again, but it's not bad for you, as we have this going on here, right? And we know that the cosine of theta is x over r, and the sine of theta is y over r. That means that x is equal to r cosine, and y is equal to r sine. These are basically the equivalent of x and y in polar form. We also know that r squared is equal to x squared plus y squared by Pythagorean theorem. This is true. Okay, so just keep that in mind, because what I have here is going to be quite interesting. So I'm going to move this down here. I'm going to actually copy this. I'm going to keep copying it so I can see it, and you need to be able to see it too. Okay, this is what I have right now in regular rectangular form. It's going to be 1 plus, what did I say, that was x squared over 25 plus y squared over 25 dy dx, and the limits of integration, this was the square root, negative square root of 4 minus x squared, and this is square root of 4 minus x squared. And with x, right, the limits of integration for x, what did we say that was? We said that was negative 2 and 2. When we convert this, we have, here's what's going to happen. We're going to convert dy dx, okay? So there's actually a formula for this, and I found it on a website. I'll link it to you right there. But here it is. When we convert a double integral to polar, here's the, I'm going to write the equation. So here's the conversion. This is all pretty good math. Okay. Alright, so we're going to convert across D, we'll call it, a function. This is z right here. This is a function of x and y. We're saying z is a function of x and y. That's the same thing as z, right? And that area of that chip right there is equal to the area, or the integral, if we convert it to polar form. We'll say from A to B, and then from C to D on the inside of this. We're just using a formula, general form of f of r. This x is now what? I told you it's r cosine theta, comma r sine theta, which is your y. And then instead of saying dA, which is the area dx dy, we always write it as r. And then you could write it as d theta dr. Technically it's d theta dr, but we're going to switch it around, because we're going to, this is for having dx dy. So really I should write this as, let me erase that, I should write this as dr d theta. That's what I should write it as, because we are doing dy first in my example. And most integrals I've seen, they do dy first, because apparently it's simpler to do it that way. So we'll write it as dr d theta. And the order in which this is done, it doesn't really matter, as long as the limits of integration match it. Inside goes to inside and outside goes to outside. So that's actually trivial. Okay, so here we go. So that's your formula we're going to make the conversion with, and I'm actually going to do that here and get this done. So here's what I really have. When I have this equation right here, when I have when I say the square root of 1 plus x squared over 25 plus y squared over 25, that's actually equal to 1 square root of 1 plus 1 over 25 factored out of x squared plus y squared. But this is really the same thing as the square root of 1 plus 1 over 25 times r squared, because x squared plus y squared, as we now know right here, is equal to r squared, right? That's what I really have there. So what I really have here is this, okay? And that's what I'm turning this into. So that's great. Okay, so let's talk about limits of integration then, okay? So for your y, we're going to draw this circle here. Again. Okay. So here's what I got. I have an integral with, double integral with two limits of integration. I don't know what they are. And the square root of 1 plus We can write that as r squared over 25 or 1/25 r squared. Let's write it like that, 1/25 r squared. And then we're going to have r. This is how it always follows. You always get r dr d theta. Dr d theta. Like that. Okay? So what actually I need to figure out is my limits of integration for r. Now if you were to draw a circle, and my circle has a radius of 2, which I've already showed you on the, I literally drew it on top of the chip. Okay, so this is the limit of the radius. And the radius, the smallest possible radius, is 0. Right there. And the largest possible radius is 2. So the limits of integration of this radius, you can't have a negative radius, so it's going to be 0 and 2. Those are my limits of integration for the radius. That's the inside integral. Now for the angle, this is a circle. So what's the smallest possible angle in the circle? That would be 0 degrees. And if I go all the way around, we'll say not even degrees, we'll even say radians. So we'll say 0 radians. And then I'm going to go all the way around the whole thing. This is going to be 2 pi radians for the whole circle. So that's your minimum 0 and your maximum 2 pi. So this will be the limit between 0 and 2 pi. And the reason I'm doing this is now this integral is so much easier than trying to do a rectangle. Using a circle turns out to be a lot easier by converting to polar form. Okay, so now what I'm going to do is a u substitution of this on the inside here. Okay, and then I will solve this integral. Okay, so I'm going to do a u substitution here. Change that. Keep trying to make a different color. So u is going to equal this right here. It's going to be 1 plus 1 over 25 r squared. We're going to take the derivative of u with respect to r, so it's going to be du. The derivative of 1 is 0, and then the derivative of this with respect to r is going to be 2 times 1 over 25, so it's going to be 2 over 25 r, and then we write dr, because it's the derivative of u with respect to r. So now the key is to solve this for dr, because that's what I have right here is a dr. So I want to solve this for dr, so I'm going to say dr. We're going to multiply both sides by the reciprocal of 2 over 25, which is 25 over 2, and then divide both sides by r, which will give me 25 over 2r du. So this is actually going to equal, dr is going to equal 25 over 2r du. And what I'm going to do is going to take this and plug it into here, into dr. Okay, so we're going to plug this back into dr, now that we found it for dr, and then we're going to substitute it and basically change it up here. So we're going to rewrite this integral. From 0 to 2 pi and 0 to 2 on the inside. This is now going to be the square root of u. Actually, I'll write that as u to the power of a half instead of the square root of u. U to the power of a half. And then here I have r. dr is 25 over 2r du is what I said. So this is going to be 25 over 2r du, and then don't forget the d theta on the end. Okay, and what's going to happen is these are going to cancel. R is going to cancel this r right there, so that's out. So what I have now is 25 over 2 times all this mess. Okay, so let's actually write it like this. I'm just showing you all my steps and being very deliberate. You probably could skip some of these, but I'm going to go very methodical. I wouldn't write necessarily all these steps if I were putting it in a report per se. Maybe I would, I don't know. Depends how long it is, but, and I have this. So I have, now we have u to the power of a half du d theta. So what I'm going to first take care of is this integral right here. We're going to take the integral of u, because this just says du, with these limits of integration. So to do that, I'm just going to add 1 to the power and divide by the new power. It's going to be pretty straightforward. Okay, so when I do that, this is going to be, it's going to be 25 over 2 times u. If I add 1 to this power, it's going to be 3 halves. And then I'll divide by the new power, which is 3 halves. This is technically what I'm doing. Okay, and we don't have that limit anymore, so we'll just put this as a brace, and then right here I'm going to have my limits of integration going on here, which is from 0 to 2. Okay, and this is not, this du is gone now, so we have this, and then we have d theta on the outside, just hanging out there, chilling out, d theta, with its limits of integration hanging out here doing nothing, okay? Yet, anyway. Alright, so this is what I'm going to write it as, blah, 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 blah. Okay, limits of integration. This right here, this will reduce. So this is like the same 2 is the same 2. This is going to be 25 over 3. Right? And we're going to write that. And this u is actually what I say u was. You have to plug it back in, the original one, which is this. It's 1 plus r squared over 25. We'll write that. So this is this times 1 plus r squared over 25. And then we'll have the limits of integration still here. And then on the outside of that, we will have my limits of integration for d theta. Still d theta out here, just chilling out, okay? Okay, so now, this is a 2. What we're going to do now is we're going to plug in the 2 into the r. And then subtract and then plug in the 0 into the r. Same thing as we always do when we do integrals. So when I do this, keep this out here. I'm actually going to distribute this first. I'm going to say this is going to be 25 over 3. The 25's cancel when I distribute that, so it's going to be r squared over 3. Plug in here and here, and then d theta. So this is actually going to work out pretty nice, as it turns out. So I'm going to plug in the 2. So I got 25 over 3. Plug in the 2, and you're going to get 4 over 3. And then you're going to subtract, and you're going to plug in the 0. So you into this whole term here. So you're going to get this minus 25 over 3 plus 0, which is just that, really, is what I have here. And then we have, hanging on the outside still, 2 pi and 0, d theta. We're almost done. This is going to cancel. So all this is really now is 2 pi 0 4/3 d theta. So all that's left is 4/3 after all that. And then we'll take that integral with respect to theta. So this will equal, oops, I keep putting the integral after I'm doing it, so I don't really need to put that anymore. I don't know why I keep doing that. This is going to equal 4/3 theta. We're just adding a theta to the 4/3 now, from 2 pi to, from 0 to 2 pi. Now we'll plug in the 2 pi, so it's going to be 4/3 times 2 pi, and then minus 4/3 times 0. And this will equal 8 pi over 3 would be your area inside that cylinder. And that's the answer you're getting. So you'll have to justify all that work, but that's the answer. And that's the answer I got for the way I've set up this problem. And that would definitely work, I believe. So that is your solution. There's all the work for it in a video, and I'll post this this actual Smart Notebook file. I'll save it as a PDF and give it to you. Okay, so you can look at all this if you want to look at all this again. But that is how I did it. I'm sorry it was so long-winded, but I was trying to be as detailed as possible.